Hi, my name is Balint Gyevnar. I'm a PhD student from the University of Edinburgh and I'm currently working at the Autonomous Agents Research Group run by Stefano Albrecht. To summarize the lengthy title of this talk, we had two goals for this work. First, we wanted to explore the role of explanations for passengers traveling in an autonomous vehicle. We tried to answer why explanations are important for vehicle-passenger interactions and how we should design them to maximize their usefulness for people. Second, we set out to create a method that can automatically generate these explanations for autonomous vehicles which are actually beneficial for passengers. But what is the point of giving explanations? The systems that comprise autonomous vehicles are totally opaque to the average passenger. It's practically impossible for them to understand how things work under the hood. Understandably, this opaqueness leads to concerns that the vehicle may fail in out-of-distribution scenarios, and this has fostered continued distrust and skepticism in the public eye, leading many people to be reluctant to accept autonomous vehicles. Now, if you would like to see AVs proliferate, then we would like people to trust and understand them. And this is where explanations come into play. Consider the following driving scenario with a two-lane single-direction road and a T-junction. The ego vehicle in blue is trying to reach the blue goal straight at the end of the road. However, we observe that vehicle 1 cuts in front of the ego vehicle and begins to slow down. If we assume that vehicle 1 is driving rationally, its most probable action is if it's trying to turn right at the junction to reach the black goal. This action is indicated with the thickest line. Other trajectories receive very low probabilities, which are then indicated by the thin lines. The ego is trying to head straight, but it would like to avoid being slowed down by the vehicle in front of it, therefore it decides to change to the left lane and continue straight there. The passenger traveling in our vehicle might wonder why the ego decided to change lanes instead of just going straight. The ego could give some complicated explanation involving perhaps optimization of rewards, but arguably that would not be very useful or understandable for the average passenger. So instead, the system would explain in intelligible terms the relevant causes behind the high-level actions of the ego vehicle. If the ego had continued straight, then it would have reached its goal slower because the vehicle in front is likely slowing down to turn right. So we have seen what an explanation could look like for a passenger in an autonomous vehicle. Researchers have argued that we can improve both trust and understanding of autonomous vehicles using explainable AI. However, it's important to design these explanations with people's requirements in mind. This human-centric way of approaching XAI has been gaining traction since the seminal 2019 paper of Tim Miller, and here we present a new framework of approaching human-centric XAI for autonomous vehicles. Our framework is structured as a pyramid. At the foundation, we have a need for transparency. Explanations should be built on systems whose purposes, capabilities, and methods are transparent. We should avoid inscrutable black boxes and surrogate model-based explanations, because black boxes are inherently uninterpretable, and surrogate models introduce a new level of abstraction which make the understanding of our systems more difficult. Explanation should appeal to causality behind the process that generated our decisions. This is why transparency is important, because it's difficult or even impossible to accurately determine causality in black box systems. And finally, our explanation process needs to be social. Explanation should be easy to understand, and the explanation process should be interactive. During interactions, we can build an understanding of the requirements of the passenger. Then we can select the causes for our explanations in a biased way that appeals to the expectations of the passenger. We call the integration of human-centric XAI systems with autonomous vehicles explainable autonomous vehicle intelligence, or XAVI for short. My essay introducing this problem and discussing how we could build a solution to XAVI won third prize in an international competition from IEEE Intelligent Transportation Systems Society. And for the rest of my presentation, I'll describe our first step towards building XAVI, a new automatic explanation generation method. This method can produce causally justified, intelligible explanations for the high-level behavior of autonomous vehicles. To satisfy the transparency requirement of human-centric XAI, we decided to use an inherently interpretable motion planning and prediction system called IGP2. IGP2 relies on intuitive high-level driving so-called macro actions such as change lane or exit road. It finds a probability distribution over the possible goals and trajectories of each other traffic participant using these macro actions. IGP2 then relies on these trajectory distributions to inform a Monte Carlo tree search over macro actions, which finds the most optimal plan for the ego. As IGP2 uses these intuitive macro actions, the authors could give intuitive explanations to the MCTS plans in terms of rationality principles. We use these explanations as baselines during our evaluation. The next step in our system is to map the algorithmic steps of IGP2 to a Bayes network model. To do this, we rely directly on the internal data structures of IGP2, which is a nice property when working with transparent systems. First, we define random variables for both the goal and trajectory prediction step. Then, we also define random variables for the steps in the Monte Carlo tree search algorithm. The structure of the Bayes network then connects these random variables such that specifying values for each random variable uniquely determines a full execution cycle of IGP2. The resulting joint distribution allows us to draw probabilistic causal judgments by conditioning on a counterfactual scenario, for example. We assume for now that passengers' queries are contrastive and parsed by an external system. The contrastive query explicitly specifies a counterfactual scenario. Using our Bayes network, we can compare the factual and the counterfactual scenario and generate a set of causal attributions which are used as input to a context-free style generative grammar that produces our natural language explanations. We evaluate our system on two driving scenarios from the IGP2 paper, although here I'll only show explanations from the first scenario, which is the scenario from before. As a recap, in this scenario, the blue ego decides to change lanes to the left because vehicle 1 cuts in front of it and begins to slow down. This would slow down the ego as well. First, we test the counterfactual scenario in which the ego doesn't change anything and just continues straight behind the vehicle in front of it. Our system correctly identifies the effect of following the counterfactual action, that being that we reach the goal slower. It can also identify that this effect was caused by the particular actions of vehicle 1. IGP2 calculates the return of a sequence of actions of the ego, not just based on time to goal, but also on other components such as jerk or angular velocity. Our system can order these in terms of their causal effect size to produce a more complex explanation. Additionally, if the vehicle in front is placed close enough to the starting position of the ego, then the ego would not be able to decelerate quickly enough, which results in a collision scenario. Our system can also identify and explain this eventuality. We also test the counterfactual scenario where the ego decides for whatever reason to turn right at the junction. Here too, our system identifies the outcome. The ego would simply not reach its goal. There are of course limitations to our work that need to be addressed in future work. Currently, we can only give the causes behind the actions of the ego in terms of macro actions. However, a passenger may inquire about why, for example, the vehicle slowed down instead of maintaining its speed. Now, IGP2's high-level macro actions abstract these trajectory details, so we wouldn't be able to give satisfying explanations to such a query. At the moment, we only support contrastive questions for why questions, but it's a natural extension then to support other forms of questions too, such as what or how questions. Automatic explanation generation methods are inherently post hoc, and the serious issue with any such post hoc method is that they may not be sound. A sound method must explain the decision process of the underlying system accurately without distorting causality or introducing algorithmic bias. We cannot claim that our system is definitely sound, unfortunately, because of the abstractions introduced by the Bayes network model, and we need for this a formal proof to show that the Bayes network model is in fact sound. Furthermore, the current system only generates explanations on an instance-by-instance basis. If we want to be truly social, as discussed for human-centric XAI, we should build the current system into a process that supports continual interaction. And finally, we need better evaluation. We need more scenarios that test explanations for both efficiency and safety-related questions. We also need to test or generate explanations with actual people. This will help us determine how people's trust in autonomous vehicles is affected by explanations, and also show us how our explanations change people's understanding of autonomous vehicles. So, in conclusion, we propose a framework for creating human-centric explanations for autonomous vehicles, and we propose a method to automatically generate human-centric explanations for the high-level driving behavior of autonomous vehicles. You can find both the paper and the code for this work under the links on the slide. And please note that IGP2 actually uses the high-fidelity simulation environment called Carla, so our explanations are also generated by running simulations within Carla. And with that, thank you for your attention.